Channel. On the day 29 of the 100 Days Digital Design series, we are going to talk about carry look ahead adder. In the previous video on day 28, we discussed about triple carry adder, and there we noticed a problem, that is propagation delay. Since the carry was going from one full adder to another full adder, we were getting a lot of propagation delay. To solve that problem, we got carry look ahead adder. Let us see how a carry look ahead adder works. See, the foundation is always going to be the full adder itself, and mathematically we know that C out expression is A dot B, that is A multiplied with D addition, C in multiplied with A XOR of B. This is the C out expression, Boolean expression for C out. Now the thing is, we'll divide this C out logic into generate and propagate. Generate, the bit will produce a carry regardless of the input carry. Means whether you give the input carry or not, it will definitely produce a carry. So that is gi will be ai dot bi, means gi is multiple of a, what do I say, like it's just an and gate. And propagate, the bit will pass an incoming carry to the next stage. Propagate is nothing but like pushing the carry to the next stage, like from one full adder to another full adder. I have that as ai, that means a xor b. So the carry for the next stage will be calculated with this formula gi plus pi, that's propagate into the carry. Let us see the step by step derivation of this thing. So the base equation is definitely this, the next stage carry equation. Now to calculate C1, that means it is the carry of the first adder. That is nothing but C1 is equal to G naught plus P naught into C naught. I am replacing my C1 here. So I'll get G1, P naught, and G naught, P naught, and C naught. Similarly, when I go to C2, my C2 will be G1 plus P1 C1. So what I'll do this, I'll replace this C1 with this. So I'll get G1 plus P1, G naught plus P naught C naught. So I'll get the resultant equation like this. I'll multiply P1 G naught plus P1 P naught C naught. Now going to the C3, we need C3, right? Now we'll substitute the C2 expression. So I have C3, I get C2 here. I'll substitute whatever was in C2. This is my C2. I'm going to substitute here, and again I'm going to multiply. I'll get this final result equation. The final carry or the final C out. So how will I get this C out? I have C4. C4 will be G3 plus P3 C3. C4 will become G3 P3 G2. That means I'm going to multiply everything and I'm going to keep it. I have multiplied C3 here. This C3 is going to be multiplied with P3. This is my final C out. So here the thing is, you generally had a full adder. So what you did in triple carry adder, as soon as you got the C out, you just gave it to the full adder. Rather than doing that, here I'm taking the C naught as an input to the carry look ahead logic. That means I'm going to have my generate, propagate, and carry. So whatever carry I'm getting here, that will be given as an input to the full adders. So what this does is, in this one clock cycle, this whole thing will get completed. Rather than waiting each clock cycle for the cout to go from one full adder to the another full adder, which took a long delay. If we had a very big number, since it's only 4 bit, it looks very small. But if you had 64 bit, and to go from cout to the next full adder, it may take one clock cycle. So for every full adder, if it takes one clock cycle, only for the carry to move forward, we require around 63 clock cycles. So that would not make any sense. So we have carry look ahead logic. Here we'll have the generate, propagate, and carry. This design, whatever we have put here, will be present here. So you will get the final C4 output here, and whatever is your carry here will be given as input to the other full adders. Now coming to the Verilog coding of this module CLA, that means module carry look ahead of 4 bit. My inputs are going to be 4 bit and input is seen 3 is to 0. I here require a 4 bit wire G, P, and C. So what is G, P, and C? It is nothing but generate and propagate and carry. This generate, propagate, and carry will all be of each 4 bits. Now, the writing is very simple. I have to tell what is G, what is P. I already know G is A and B, P is A XOR B. So what I am going to do is, I am going to write down the equation directly. So I know that my C naught here is, first one will be equal to C in. C naught is C in. Whatever I'm giving it as input, that will be the C naught. C1 is not like that. C1 will be G naught. Where is C1? So yeah, C1 will be G naught plus P naught and C naught. So I have to write the same. In a similar way, whatever is your final resultant equation, these equations, we'll put it in the form of code. That is what I have done here. I have done the same for C1, C2, C3, and then the last output will be C out. And now I have to assign my sum, right? Sum is nothing but whatever was your propagate XOR again with C. Nothing but you already know that what is sum for a full adder? It is A XOR B XOR C. What I'm doing is here I'm first calculating the propagate A XOR B, then I'm going to replace it in sum. So it is the same procedure, nothing has changed. Now to write the test bench, I write module test bench CLA 4 bit. Register is 3 is to 0, the same thing. Whatever is my input, I'll register it and wire will be given as out. Now I have to instantiate the unit under test. This is my unit under test, that is CLA 4 bit. So I am instantiating the inputs here and outputs. Initial begin. I'm using these two lines specifically because I'm using Aldeck Rivera Pro. To get the waveform window, I need to put these two lines, or else I'll not be getting a waveform window. Dump.vcd and dump VRS. Both these lines are very important to get your waveform. Now dollar monitor, time is percentage 0t. This is a monitor statement. A is equal to percentage B, that means it will be in binary. B is equal to percentage B, it will be in binary. C is also percentage B. So it will all be in binary. Sum is equal to percentage B, C out equals percentage B, and dollar time. Now we have given the order A, B, C in sum and C out as per this. It will also give me the time. So it is dollar time. Now I'm giving my test cases. In the first case, I have 0011 and 0100. What is that? It is 3 and 4. So the output has to be 7. Am I getting 7 here? Yes. Here again the same thing. 4 dash B111, that is 15 plus 1. 15 plus 1, it has to be 16. So what happens when you write 16 is the sum becomes 0 and C out becomes 1. It is because when you add both of the things, the 4 bits will become 0 and last fifth bit will become a carry bit and that will turn 1. So you will get 16. The test case 3, all inputs will be high. So A is equal to 4 dash B1010, that is 10, and here it is 6. Okay. And Cin is 1. See, the one things I have changed here is Cin is 1. So what happens? 10 plus 6 plus 1 is equal to 17. This is one change that we have observed here. Let us see it in the waveform. 3 plus 4, 7. And here it's F plus 1. That is F is your 15 plus 1, 16. One carry bit is raised and sum is 0. Is it correct? That is what we wanted, right? 111001. Cin is 0. Sum is also 0. C out is equal to 1. Now we'll go to the third. Here what happened was in the previous two test cases, I gave my Cin as 0. But here I am telling Cin is equal to 1. That means there is already carry input that I am giving. So A is 10 and 6, 10 plus 6 plus 1. So you need to get 17, right? So here I have already one carry out reached. The carry out is 1 and sum is 1. So it will be equal to 7. 17, sorry, 17. That means my output will be 0001. C out is equal to 1. I'm getting that right? Yes. C out is 1 and sum is also 1. Now let us go to the EDA playground. I've written the same code here. I'm just going to tell you how to simulate it. As I've already explained the code, just save the file. Then see that it is system verilog and verilog. Here I'm using Aldeck Rivera Pro. Time scale is I'm not given, but it's okay. Just copy here and before your test bench, you can give it. Not a problem. And press open EP wave after run. Then you can run the code. Okay, let's not do it this now. It's giving some problem. Without that also we can run it. Let us see. Yes, I've got the output and I'm getting my waveform also. So if for you, since you're doing it for the first time, you may not get this waveform. What you have to do is you have to go to get signals, press on TBS CLA 4-bit. You just need to press shift, um, arrow down, and up and all. So yeah, you got all your outputs here. Now you might have a question where whether my whereas my in whatever I'm given in the code is in binary, but here in the waveform it is all coming in decimal or hexadecimal. Why is that? So what happens is your waveform window has a mode. It is always set in hexadecimal. Just go to this, press binary. So you'll easily get whatever was your numbers in binary, 111 and 1. So you'll get the same thing. Thus you can verify your waveform. Thank you. If you have any doubts, feel free to put it down in the comment section.